The final lesson, section 10.5, area and arc length in polar coordinates. The area of a polar region is based on the area of the sector of a circle. If you recall, when you learned area of a sector, portion of a circle, and we wanted the area of that sector right there, it was theta over 360. In this case, we'll do 2 pi, but your theta was this length, theta over 2 pi, times pi r squared, the portion of the circle times the area of the circle. And this became 1/2 r squared theta. So if we take a function where r is a function of theta on the interval from alpha to beta, so here I have a polar curve from alpha to beta. You can see I can divide this into lots of little almost triangles. Here is the first radius, here's the next radius, here's another radius, here's another radius, the radius going to a point on the curve. And what I actually get is my central angle is the kth sector, so beta minus alpha over n, number of subdivisions, is my delta theta. And so my area is approximately the sum, as k goes from 1 to n, oh, we've seen that before, of 1/2 r squared times the change in theta. This is a Riemann sum. And this Riemann sum, as the limit as the number of divisions goes to infinity, becomes this nice little integral. If f is continuous and non-negative on our interval from alpha to beta, then the area of the region bounded by the graph of r equals f of theta, my function of theta, my polar curve, and the radial lines theta equals alpha to beta, is given by the area 1/2 integral alpha to beta r squared d theta. And again, as I always say, let me get through the whole explanation and then you can write it down at an appropriate time. So here's our old friend, r equals 3 cosine 3 theta that we looked at recently. We know that around the circle is 360 degrees divided by 3 means that my petals are 120 degrees apart. Remember that if that number is odd, that is the number of petals you have. If it's even, it would be twice that number of petals. What we want is 3 theta to be unit circle numbers. We need to find where one petal starts and stops. And it turns out, if we go from negative pi over 6 to pi over 6, we will get 1 petal. We know that at pi over 6, I'm at 0, so negative pi over 6 to pi over 6 will give me that petal. So how do I know this? I'm going to play with my numbers, but I've seen enough that I can see what's happening. This is 0, and this happens at pi over 3. So we can see by making a theta and a radius theta chart, we get this. We did this the other day. So since I'm going to go from negative pi over 6, which takes me here, to pi over 6, which takes me here, 1/2 negative pi over 6 to pi over 6 is r squared d theta. Now we know how to do this algebra. First of all, I'm going to, since I can see this here, instead of negative pi over 6 to pi over 6, what if I just went from 0 to pi over 6 and doubled it? So I'm going to do that because that's going to be easier. And now let's take 3 cosine 3 theta squared. Well, that's 9 cosine squared 3 theta d theta. Do you remember our power reduction formulas from a few chapters ago? So cosine squared of an angle is cosine of twice the angle plus 1 divided by 2. Now let's notice my angle is 3 theta. So twice it would make that a 6 theta when I do my substitution. I'm going to bring the 9 out. The integral from 0 to pi over 6, 1 plus cosine 2 times 3 theta over 2 d theta. I'm going to make two separate integrals here and look at 9 from 0 to pi over 6 of 1/2 d theta plus 9/2 cosine 6 theta d theta from 0 to pi over 6. Okay, this is easy. I can make this 9/2 0 to pi over 6 d theta plus, let's look at this. My u is 6 theta. My du is 6 d theta. I need that factor of 6. So I'm going to multiply and divide by 6. You know how to do that. That is going to actually give us outside of here, when I reduce everything, 3/4. Here I have the cosine u du form. I am not going to change it because I don't want to mess with having to change the limits. But we can see this is easily going to integrate to theta. This is going to integrate to sine of 6 theta. 9/2 theta from 0 to pi over 6 plus 3/4 sine of 6 theta from 0 to pi over 6. Do our fundamental theorem step, do the work, there's our approximation. Here's our area, which can be approximated here. Okay, pause the video and write down this work and recognize that this is going to continue onto that other page in a moment. Here is the rest of that problem. Just in case you've forgotten your double angle identities, you might want to write this down. Again, you can, from here, you can get the two that you need, our power reducing identities. Next example. Find the area of the region inside the inner loop of r equals 1 minus 2 sine theta. Now, this is a limosome. If r is 0, the point is at the pole. So if I make a table, I can start to see some values. From the table, you get the limits of integration because this is going to be where the inner loop starts and stops. Okay, so pi over 6 to 5 pi over 6. So my area is 1/2 from alpha to beta r squared d theta. Okay, that's our formula. From pi over 6 to pi over 2 and pi over 2 to 5 pi over 6 is the same distance in my path. So I'm going to double pi over 6 to pi over 2. And when I double that, the 1/2 goes away. Also, what I can see is that 1 minus 2 sine squared theta is going to multiply out to this. I can see that it would be nice if I didn't have this sine squared because that is difficult for us to anti-differentiate. But I can do it if I do a power reduction identity. And now we have aloha going on. And I'm going to do that integration. Here's my aloha. 1 plus 2 is 3. I'm going to make that its own integral. Minus 4 sine theta d theta, and then minus 2 cosine 2 theta d theta. And I notice that if my u is 2 theta, my du is 2 d theta, so I'm just going to regroup and move this 2 down here. So each of these pieces has their own little integration, and I'm going from pi over 6 to pi over 2, which is going to give us this ugly answer. And how we got to that answer was substitute pi over 2, do a lot of simplifying, substitute pi over 6, do a lot of simplifying. Now what is going on is we are finding the area of this inner loop. Now how did I know what this was going to look like? Well, first of all, it's sine, so we're going to reflect across the y-axis, and it's negative sign, so we're going to go down instead of up. And we know it's a limosome with an inner loop because of my ratio of A, which is 1, to B. And A to B is less than 1. So that's how we know. Okay, take a moment to write all of this work down. Okay, again, let me explain the work and then you can write it down at an appropriate time. Find the area inside r equals 3 sine theta and outside r equals 2 minus sine theta. Now this we should recognize. That's a circle. diameter of 3 on the y-axis. That's that part. What about this one? This is 2 minus sine of theta. It's going to be, like for instance, when theta is pi over 2, sine of pi over 2 is 1. 2 minus 1 is 1. So on the pi over 2 radial arm, I go up to 1. And it is a limicon. And this is a limicon because the ratio of A over B is greater than 1. So it's going to look like this. Now, I need the area inside the circle, but outside the limicon. Here's my circle. So inside the circle and outside of this. So that's this shaded green region. So our radial lines, these are really important. We're going to think of these like windshield wipers, sweeping out what I want. So I want to go from here to here. I'm sweeping out. Okay? This is what I want. So I need to know those points. So we need to look at where does 3 sine theta equal 2 minus sine theta. That's going to give us 4 sine theta equals 2, or sine theta is 1/2. So our angles are pi over 6 and 5 pi over 6. Now, from the pole, if I take pi over 6 to 5 pi over 6, that gives me all of that. I don't want all of that. I need to get rid of that part. So I need to integrate from pi over 6 to 5 pi over 6, the circle, which is going to give me this part, minus the limicon, which is going to take away that part. 1/2 pi over 6 to 5 pi over 6, r squared d theta. So this is my circle, minus 1/2, 2 minus sine theta squared d theta. We have a lot of algebra and trig, but guys, I want you to do this on your calculators. You need to be able to do this on your calculator, especially being able to find the integral. All right, you can certainly do this by hand. I didn't do it by hand just because. All right, so if you want to take a moment and write down this work, there you go. Find the area of the common interior of r equals 3 minus 2 sine theta. So we know that's going to look similar to the one above, except that it is a 3, and 2 sine theta is going to elongate it, and we're going to be hanging down and reflecting across the y-axis on this one, or the pi over 2 radial line. And r equals 3 minus 2 cosine theta. This is going to be reflecting across the pi radial line. And this is what we have. So let's graph this one. Again, I can do it with just a few points. Okay, so this is my radial arm on 0, at pi over 2, at pi, and at 3 pi over 2. So let's look at this one. Sine of 0 is 0, 2 times 0 is 0, 3 minus 0 is 3. So at 0, my 0 radial arm goes out to 3. Sine of pi is 0, so on the pi radial arm, I go out to 3. At pi over 2, sine of pi over 2 is 1. 3 minus 2 times 1 is 1, so on the pi over 2 radial arm, I'm at 1. And at 3 pi over 2, sine of 3 pi over 2 is negative 1. 3 minus 2 times negative 1 is 3 plus 2. So on 3 pi over 2, I'm at 5. And I know that the shape of this is going to have a little indentation there. Okay. Now let's do the same for this. At 0, cosine of 0 is 1. So 3 minus 2 on the radial arm of 0, I'm at 1. And I know this is going to reflect across the horizontal axis here. When cosine of pi is negative 1, so 3 minus a negative 2 takes me to the 5 on the pi radial arm. At pi over 2, cosine of pi over 2 is 0. So this will take me up to 3 on the pi over 2 radial arm. And at 3 pi over 2, cosine is 0. This will take me down to 3 on the 3 pi over 2 radial arm. Now, what is it we're looking for? The common interior. In other words, where they overlap. Okay, so I want this. Now, I need to find where these two intersecting points are. I need these 2 points. And you'll notice that once I have those 2 points, it looks like these are mirror images across that line. And so I only need to probably integrate one part of the region and double it. But I need to find, I can see that this is 5 pi over 4 and pi over 4, but I actually need to analytically find it. So if I go from pi over 4 to 5 pi over 4, it just gives me half of the region. So I need to double that to get the full region. So again, my formula, 1/2 integral from alpha to beta, r squared d theta only gives us half the region. We must double it. So that is going to give me this. The work is left to you. There's the answer. So now, if you would like to pause the video, you can write down this work. The last page of the last formal lesson. Look at that. Okay, to find the length of an arc in polar form, arc length, we start with this parametric formula. Remember that one? And instead of t, we're going to replace it with theta. And we're going to go from alpha to beta. That's our angles. Okay? Now, we know that x is r cosine theta. So we know dx d theta is once again negative r sine theta plus r prime cosine theta. And since y is r sine theta, we know dy d theta is r cosine theta plus r prime sine theta. Now, let's look at this formula. We are going to take the r equation and change it to parametric form. Here is dx d theta squared plus, here is dy d theta squared. Now we know our algebra, a plus b, the quantity squared, is a squared plus 2ab plus b squared. And I'm getting ready to do quite a bit of work. So again, let me give the entire example before you write the notes down. I have a couple of rightos in here that I have fixed in your lecture manual. All right, here we go. This quantity squared gives us all of this. Now, let's look. Squaring this, r squared sine squared theta, it would be a minus because it's a minus times a positive. 2ab, so 2ab gives us all of that. There's the cosine theta I left out, but is in your book. Plus b squared, this squared. R prime squared times cosine squared theta. All of that is your dx d theta squared. Plus, that is this. So this squared is r squared cosine squared theta plus 2 times r prime cosine and sine theta plus r prime squared sine squared theta. D theta is outside of the square root sign. Now this is dy d theta squared. What I can see is that I have r squared and sine squared plus cosine squared. Plus, I have r prime squared, sine squared plus cosine squared. And notice that these two terms have opposite signs, they drop out. Now what do I know about sine squared plus cosine squared? You guessed it, that's 1. So now I'm looking at the integral from alpha to beta, the square root of r squared plus r prime squared d theta. Dun da da. What do we know about r prime squared? It is dr d theta squared. So you're going to add this to your list of formulas you have to know. There you go. That is your length of an arc in polar form. Yes, you need to know it. Okay, guys, the last example of the last lesson. We're going to find the length of the arc from theta equals 0 to 2 pi for this cardioid. Again, let me explain the problem all the way through before you write it down. So my arc length S is from 0 to 2 pi r squared plus dr d theta squared d theta. By the way, this is not square root of this squared plus this squared is not 2 minus 2 cosine theta plus 2 sine theta. That's very bad math. That is not that. We're going to do the work. 2 minus 2 cosine theta squared gives me 4 minus 8 cosine theta plus 4 cosine squared theta. Squaring this gives me plus 4 sine squared theta. Ooh, I can factor out a 4 and I get a 1 there. Okay, I have negative 8 cosine theta plus this 4. Factor of 4 out here gives me 4 times cosine squared theta plus sine squared theta is 1. So now I have 4 plus 4, which is 8. So I have 8 minus 8 cosine theta, again from 0 to 2 pi d theta. And I can factor out the 8. Square root of 8 times 1 minus cosine theta d theta. This continues. From the previous page, that 8 can come out from the square root and become 2 times the square root of 2. What do I do with 1 minus cosine theta? I can't make that my u, because if u is 1 minus cosine theta, I need sine theta somewhere in there, and I don't have that. So now we have to go back to our identities again. Let us remember cosine squared a minus sine squared a is cosine of 2a. If I do a substitution for cosine squared of 1 minus sine squared gives me 1 minus 2 sine squared a times cosine 2a. Solving this for, let's give me 1 minus cosine 2a equals 2 sine squared a. Let our a be theta over 2. Ooh. So 1 minus cosine of theta would give me 2 sine squared theta over 2. Okay, look at that again, because I need it to be cosine of theta. So let's let our a here be theta over 2. The 2's will cancel. I'm left with 1 minus cosine theta. And that can be written like this. So 2 sine squared theta over 2 is going to go right here. Well, the nice thing about that is I get square root of 2 times the square root of sine squared of theta over 2 d theta. This square root of 2 can come out here with that and be 4. The square root of the sine squared of theta over 2 is sine of theta over 2. Ah, yay! Okay, let's think about this. If my u is theta over 2, my du is 1/2 d theta. So sine of u du is sine of theta over 2 times 1/2 du. How am I going to do that? I'm going to multiply inside by a half and outside by 2. And so the antiderivative comes all the way up here. 8 times negative cosine theta over 2 from 0 to 2 pi. Okay, substitute 2 pi. I'm going to bring that negative out. Substitute 2 pi for my theta gives me cosine pi minus cosine 0, which is negative 8 outside times negative 1 minus 1. Negative 8 times negative 2 is 16. Again, that number has to be positive because it's the length of an arc. It's got to be a positive value. So if you would like to write down this problem, here's the first part of it. Here's the second part of the example. And your TPs for this section, 1, 7, and 17. See you next time.